Hey guys, this is Mrs. Harbin, and this is Pre-Cal Chapter 3. We're looking at 3.2 exponential functions, and this is a second part to that first video. The first video that I made went through the examples in the book, but I feel like it didn't really explain things, terminology, vocabulary, or patterns very well. So we're going to take a quick look, a more in-depth look at exponential functions to make sure you guys understand foundationally what you're doing before you try to work through these problems in the book. So just a quick function review. We looked at this in 3.1, part 2, our different functions that we've looked at so far. We have our linear functions, which we know are going to be either straight lines with a positive slope or straight lines with a negative slope, and they'll be written in that form: ax plus by equals c. So our degree of our linear function is just 1. And then we looked at constant functions. That's where f of x equals a number, or y equals a number, and those look like horizontal lines. We don't have vertical lines included because that would not be a function. It would fail to pass the vertical line test. Then we have quadratic functions, and that is when the degree of our function is 2. We get that x squared term in there, and those functions look like parabolas. Whether they are both tails up or both tails down, we've got a parabola. The fourth function we looked at was a polynomial function, and polynomial functions can include the previous functions that we've already mentioned, but they can also have a higher degree than just x squared. They could have x cubed, x to the fourth, x to the 27th power. So polynomial functions might look like these three, or it might have some more curves in it, and we can have both tails up, both tails down. We can have left tail up, right tail down, right tail down, left tail up. We can have all of these different behaviors depending on the degree of the function, the leading coefficient, and we looked at that in the previous chapter. Last class we looked at power functions, and power functions, if you remember what a power function is, hopefully you remember, that's when our base is our exponent. And we've got a power that could be 2, 3, 4. We'll do, x squared here. And a power function is different from a polynomial or quadratic function because a power function only has one term. So a power function could be a parabola, but it doesn't have to be a parabola. But the important thing to note there is the one term. Today we're learning about the next type of function, which is an exponential function. And the formal definition for an exponential function is this. It's a function of the form f of x equals c times a to the x, where c, a, and x are real numbers, and c is greater than 0, a is greater than 0, and a is not equal to 1. So c is going to be a constant number, a is going to be our base, and x, our variable, is what's going to be the exponent. We need to remember that c is going to be greater than 0. If c is less than 0, then what happens is our function is actually flipped upside down over the x-axis, and it's no longer an exponential function. And we'll take a look at that, what that looks like here later on. A is also going to be greater than 0. A is our base there, for various reasons that we'll get to later on in this course. And then a is not going to be equal to 1. If a were equal to 1, it wouldn't matter what our x is, because it could be to the 4th power, to the 27th power. 1 to the 4th power is the same thing as 1 to the 27th power. So our f of x would just always be constant. And that's not what an exponential function is. That's a constant function. So we need to remember these parameters here for our exponential functions. C is greater than 0, a is greater than 0, and a is not equal to 1. Again, we will take a look at what happens when our c is not greater than 0, but it does cease to be an exponential function at that point. A quick note about the difference between power functions and exponential functions, because in both of these we do have a base and we do have a power. But here's the distinct difference. A power function, the base is our unknown, and we do know the power. We know that it's being taken to the 4th power. It's a 4th degree function. In an exponential function, we know our base, that's our a, which must be greater than 0. And what we don't know then is our exponent. That is where our variable is. So they look similar because they both have bases and exponents, but they are different, so be aware of that difference. Exponential growth means that the value of the function increases exponentially as x increases. And when we're looking at exponential functions, if our a value is greater than 1, we've got exponential growth. So let's say we've got f of x equals 4 to the x power. That represents exponential growth, or 2 to the x power, or 100 to the x power. All of these are going to represent something growing exponentially, and we talked in class how a good example of that might be bacteria or viruses, which do grow exponentially. Exponential decay is represented, or that means that the value of our function is decreasing exponentially as x increases. And our a here for exponential decay would be between 0 and 1, greater than 0 but less than 1. So this might look like 1/2 to the x power, or 1/4 to the x power. Those would represent decay. On a graph, exponential growth is going to take on this shape, and exponential decay is going to take on this shape. So you can see here as our x increases this way, our graph is growing exponentially. And here, as x increases, our graph is decreasing or decaying exponentially. So we can see those two shapes, and we need to be aware that those are related to that a value. That's what's telling us whether we have growth or decay. Some characteristics of an exponential function that you need to be aware of. First of all, the domain of exponential functions is all real numbers. If you take a look to the left and a look to the right, you can see that these both tails of this graph will just keep on going and getting wider and wider and wider. So our domain is all real numbers. And our range is that y must be greater than 0. There are no zeros. It does not cross the x-axis. In fact, when we have this line or this coordinate, if you will, that our function never crosses, that's called an asymptote. And we do have an asymptote, a horizontal asymptote at the x-axis. Functions can have vertical asymptotes and other asymptotes that you'll learn about as well, oblique asymptotes. But when we're talking about exponential functions, it has only that one horizontal asymptote at the x-axis. This line will get closer and closer and closer and closer to 0, but it will never actually cross or touch that x-axis. Think of it as kind of like an invisible force field. It will never go across. All right, here are 3 different exponential functions. Again, taking a look at the characteristic of an exponential function, you can see we've got our definition up here. C for a constant times base raised to an exponent. And in each of these, our constant is 1. This is 1 times 10 to the x, 1 times 2 to the x, and 1 times 3/2 x. All of our a's are greater than 0 here, or greater than 1, I'm sorry, greater than 1, and so that represents exponential growth, as you can see. And they all cross at this 0, 1, because our constant is 1. And if our x were 0, let's plug in 0 here, we would have 1 times 10 to the 0 power. Well, anything to the 0 power is 1, so this is 1 times 1, which is just 1. And we could do that for all 3 of these functions. If we plug in 0, we're going to get 1. Anything to the 0 power is 1. And so that's why they all cross at that 0, 1 point. But what's different about these actual functions is how sharp the curve is, the curvature of the function. You can see that when our base is 10, we've got a much sharper curve than when our base is 3/2. That function that's got a 3/2 as its base is much more gradual than this function that has the base of 10. So keep that in mind when you are graphing these functions. You can take a look at the base. The larger the base, the sharper the curvature there. So another characteristic to note. As a reminder, exponential functions have no zeros. The x-axis is a horizontal asymptote of an exponential function. Now you can see here we've got a linear function at 50x, and that does cross the x-axis. But when we add in that x cubed, you can see an x cubed function here, which is a power function, will go down. And you can't really tell on this, but it will go through the origin and start to go down here into the 3rd quadrant. However, 2 to the x power is going to stay above that x-axis. Even though it looks like it's right on it, it isn't actually touching it. All right, a couple of other things that you need to be aware of. Some of this might be new information, but you need to be aware of what a natural exponent exponential function is. And a natural exponential function looks like this. F of x equals e to the x, where x is a real number. And e is kind of like pi. It's this irrational but predetermined number. You have a button for it in your calculator, and it approximates out to 2.7182818 ... It keeps on going. That's what makes it irrational. So whenever you see these natural exponential functions, you will need to use that button on your calculator that looks like that. The natural exponential function is the inverse of the natural log function, which is f of x equals ln of x, or natural log of x. Now, if you've not been introduced to natural logs before, this is coming up in chapter 4, and we'll go into it in more detail. Really what we're practicing with in this particular section when it comes to the natural exponential function is using that function on our calculator. We'll go into more detail about what natural logs are when we get to chapter 4. So let's take a look at this example. You've got f of x equals e to the x. Find ordered pairs using a calculator, and when you plug in those three x values, -3, -1, and 0, you get these three y values. And when we put that on the graph, you can see that our function is exponential growth here. If you remember what our e value was worth, that e was 2.718 ... That is greater than 1, so that does represent exponential growth. Again, our constant is just a 1, so you can see our x-intercept is at 0, 1 right there. So that's a look at our natural exponential function. Hey, a couple more notes. When c is less than 0, I already mentioned before, the function is reflected over the x-axis, making it no longer an exponential function. We're going to take a look at what that would look like. Negative exponents indicate reciprocals, and fractional exponents indicate radicals. And hopefully this is a review. But let's say you see 2 to the -1/2. You've got 2 with a negative exponent. What that means, or 2 to the -x, let me do it this way, 2 to the -x. That -x means we need to take a reciprocal of our base, so that would just be 1/2 to the x power. So negative exponents mean we need to take the reciprocal of our base. Fractional exponents indicate radicals. So x to the 1/2 means x raised to the 1 power with an index of 2 in the radical. So that's just the square root of x. Anything to the 1/2 power is just the square root. X to the 2/3 power is x squared, and our radical has an index of 3. Hopefully you've seen that before, and that's a review, but let's take a look at putting that to work in a function. So here's our function, f of x equals -2 to the -x plus 3. Find f of 0, f of 1, and f to the -1/2. You can see we've got a negative constant, so we know right away this isn't going to be an exponential function, but we're going to use some information that we know about exponential functions to graph this. So when we evaluate f of 0, f of 1, and f to the -1/2, we're going to get these values. Take a really quick look at that negative exponent. So we had -2 to the -1/2 plus 3. Those two negatives make a positive, so we get -2 to the 1/2. Remember we said that a base with a fractional exponent is just a root here, so this is to the 1/2, or the square root of 2. Because that negative is not inside parentheses here, it's going to stay outside. This is -2 to the 1/2, not -2 to the 1/2. So we end up with those three coordinates, if you will. And when we first graph those, disregarding that -2 there, if we just had regular 2, we would get a function that looks like, let's see, it would cross at our 1 and here, and it would look something like this, right? But because it's a negative coefficient, it's going to be flipped over that x-axis. So adding that negative coefficient is going to flip it this direction. So we go from exponential decay to flipped over that x-axis. And then adding that plus 3, That transformation is going to slide us up 3 units here. Let me see if I can change colors, which makes our final graph look something like this. Again, not an exponential function,